Okay, chemists, in this lesson we're going to look at the shapes that molecules exhibit in 2 dimensions, 3 dimensions, depending on how many atoms are attached. We're going to start off by talking about what are called the main electron geometries. This has to do with how many electron regions are surrounding a central atom. So if I have an atom with 2 electron regions, in this case 2 bonded atoms, that's called a linear electron geometry. When you get to 3 regions or 3 domains, that's called a trigonal planar. Once you get to 4, now we're headed to 3D. This is called a tetrahedral geometry. 5 regions is called a trigonal bipyramidal. That's because if you connected all the atoms, it looks like 2 triangular pyramids, just face to face against each other. And then the last one with 6 domains is called octahedral. Even though octa might make you think of 8, it's octahedral with 6 because if you connect all of the atoms that are bonded to that central atom, you get an 8-sided figure, which is called an octahedron. So that's where the names come from. Those are the parent electron geometries. And we could model them with this simulator that I have from the University of Colorado. Here is a system with just 2 electron regions around that central atom. You can see that that is indeed linear. If I put a third one on there, you get to a trigonal planar system. We're only in 2 dimensions here. Once I add a 4th one, then they separate because of the electron pair repulsion, and we get a tetrahedral geometry. A 5th one gives me a trigonal bipyramidal, and then all 6 sites occupied, you get an octahedral geometry. And these are all adopted this way because of the repulsion between the electron pairs that are bonded to the central atom. Electrons have negative charges and they're repelling each other. So these are the best geometries you can get so that they spread out and stay as far apart from each other as possible in space. Now, outside those 5 electron geometries, octahedral, trig bipyramidal, tetrahedral, trig planar, and linear, they're also what are called molecular geometries. And many times they have the same name, but sometimes I have a different name, and what happens is if you have a lone pair instead of a bonded atom, it still has the same electron geometry, but the molecular geometry gets a different name. That's also called the shape. So let's go through some of the common shapes that we see. That's what's in this big chart down below. So the first one is when you have a central atom attached to 2 others. This is called an AX2 system, meaning 1 central atom and 2 other bonded atoms to it. And that's still a linear shape. And if it's linear in the electron geometry, it's linear in the molecular geometry as well. However, for a system with 3 domains, if you have a central atom A and 3 bonded atoms X3, that's still called trig planar, just like the electron geometry. But if I replace one of those bonded atoms with a lone pair, here in sulfur dioxide you have 2 bonded atoms and 1 electron pair that's not bonded, then we call that an AX2E system, meaning central atom, 2 bonded atoms, and an electron pair, so it looks something like this. That's called a bent molecule. And that's simply because it makes kind of a bent shape. You know, it's not linear. That's the reason for using that word. Pan over to the right and we get to the 4 domain systems. There is the possibility of an AX4, or if you replace one of those bonded atoms, you get an AX3E. Replace 2 of them, you get an AX2E2. The first one, just like the other 2 categories, is the same as the electron geometry. This is still called a tetrahedral shape or tetrahedral molecular geometry. But with a lone pair in place of a bonded atom, now we get what's called a trigonal pyramidal. And that's because it simply makes what looks like a pyramid with a triangular base when you connect all the atoms. In other words, the molecular geometry is all about the shape of the molecule made out of the atoms themselves, not including an electron pair in a separate domain. But that electron pair is causing that shape to exist. An AX2E2 system is just a bent shape. So water is bent, ammonia is trig-pyramidal, but methane is tetrahedral. So if you have the same parent electron geometry, you have the possibility of multiple molecular geometries, and that's what these are. So these are the molecular geometries. But all of these fall into one category of an electron geometry, and in this case, it's the tetrahedral. In fact, let's go through and label the rest of them right now. That first one we already did was the linear category. Right below it was the trig-planar. I'll just write a triangle. So of the original 5, there's 2 left. There is our trigonal bipyramidal category, and then there's our octahedral category over here on the right. So those are our 5 parent geometries that are all electron geometries, and within them we have shapes. So hit pause for a second and look at the remaining examples that you see in front of you for the last 2 categories, and see if you could write the classification of each one. That should be pretty easy to do, but go ahead and just fill out what should go in this column for the classification of those 7 examples we still have to do, and then we'll talk about the shapes. Okay, so getting to the trig bipyramidal, the first one is a central atom with 5 bonded atoms. Then we have a central atom with 4 bonded atoms and 1 lone pair, so AX4E. Central atom, 3 bonded atoms, 2 lone pairs, AX3E2. And then lastly, the opposite, AX2 and E3. Just for completeness, I'll do the other 3. This would be an AX6. This would be AX5E. And then AX4E2. These are the ones that one should know for this level of the class. Okay, well the first one in each of those categories is the electron geometry. This is a trigonal bipyramidal shape. And this one over here, AX6, that's an octahedral shape. So again, the molecular geometry can match the electron geometry, but once you put electron pairs, changes the map a little bit. Let's fill in the 5 coordinate system first. SF4 sulfur tetrafluoride, we actually call that a seesaw shape, because if you look at it along its edge, it kind of reminds you of a teeter-totter. So it looks like those things in playgrounds with people on either side of this sitting in chairs, and it can go up and go down, and they just call it what it looks like. If you take away another bonded atom and put a lone pair in its place, you get this shape of a molecule. It's actually 2-dimensional, and it looks like the letter T, so they call it a T shape. Take away one more atom and put a bonded, an unshared pair of electrons, and you get a straight line. So the last one in this box is actually linear. Then our last category, if we have sulfur hexafluoride, it's octahedral, but this antimony pentachloride thing, this makes a pyramid, but unlike some of the other pyramids, this has a square base, and we call it that. It is a square pyramidal. And then speaking of squares, xenon tetrafluoride just makes a square, and it's a plane, so they call it square planar. So those are all the geometries that you're going to see, at least in this class. There are others, but that's the main batch that one should know at this level of the class. So let's practice and do a few. And then the homework on the back will teach you a little bit about what's called polarity. And I'll actually comment on that before we close out for today. So phosphine, pH3. In fact, it's never a bad idea to remind yourself of the names of these things. pH3 is phosphine, NO2-, that's nitrite. CF4 carbon tetrafluoride, and SeO2 would be selenium dioxide. So, let's draw one, and let's see if we could actually draw it a little bit in 3D. Phosphine with phosphorus and 3 hydrogens attached would look like that at first, but I can tell that's going to be an AX3E, so this is going to be a pyramidal molecule. And what we do is we start to show some depth in our drawing where we can. You don't have to stick to this rule, but if the line is just a regular line, that means it's in the plane of the page. And if it's a bolder line, like this H in the lower right, that actually means it's coming out of the page toward you, and this dashed line is implying that it's going back into the page behind you. So that's a way we show 3D in 2 dimensions, by just drawing it. The type, the classification, this would be an AX3E. What electron geometry would be tetrahedral? But the shape would be trig pyramidal, just like ammonia. If I check the next one, nitrite, NO2-, that's a nitrogen in the middle. You'll get a single bonded oxygen and a doubly bonded oxygen, a lone pair on the nitrogen, 3 lone pairs on the singly bonded oxygen, 2 lone pairs on the other one, and there is overall a 1- outside the brackets. Or alternatively, formal charges. If you're learning about formal charges, we would put a formal charge of -1. It happens to be on the oxygen. Notice the 1 formal charge adds up to the sum of the charge in the formula. The type of this would be an AX2E, 2 bonded atoms, 1 lone pair, so AX2E. I look up above, that is the trig planar electron geometry, but this is a bent molecule. So hit pause and see if you could figure out what carbon tetrafluoride and selenium dioxide look like for the rest of that table. Okay, carbon tetrafluoride would be a central carbon with 4 fluorines. This would also be in 3D if you're drawing the shape. I'm going to leave out, well, no I'm not. There are lone pairs on all those fluorines. And that's the correct structure. That's a tetrahedral electron geometry. That happens to also be a tetrahedral shape. So sometimes the... Oh, whoops. I didn't talk about the classification, did I? It is a electron geometry and tetrahedral shape. The type is just AX4. I accidentally skipped that column. There we go. Selenium dioxide is a selenium in the middle. Selenium is right below sulfur, which is below oxygen, so you get something that looks just like ozone or sulfur dioxide. There's a singly bonded oxygen, a doubly bonded oxygen, and a lone pair on the selenium. If you figure out the formal charges, there would be a -1 on the oxygen and a positive on the selenium for this structure. So overall, no charge. If you didn't include those, that is okay. Maybe you haven't actually learned about formal charges yet. The type, regardless, would be an AX2E. So this is a trig planar electron geometry, but a bent molecular geometry, which means it looks just like nitrite, and indeed it does. Same number of atoms and same electron count, if I go and figure out the electron count. Now the polarity column was already filled in because we haven't talked about polarity yet. Polarity is due to an asymmetric arrangement. And there's a useful mnemonic to help us remember this. And it's SNAP, SNAP. And what that stands for is if you are symmetric, then you are non-polar. But if you are asymmetric, you are polar. So easy to remember in a SNAP. So which ones are symmetric? Well, it depends on what's around the central atom. What's easier to identify is the things that are always going to be not symmetric. So the bent molecules are never going to be perfectly symmetric because of those lone pairs causing the bending of the molecule. Likewise, the seesaws and the T-shaped molecules and the square pyramidals will always be somewhat asymmetric. The others, trig pyramidal as well. Trig pyramidal is always going to be asymmetric. So these are always going to be polar. So highlighted equals always polar. The remainder of those categories may or may not be polar depending on what's attached to that central atom. So carbon dioxide is nonpolar because these two polar bonds cancel each other out. However, carbon disulfide would be polar because the polarity of the CO bond is not the same as the polarity of the carbon-sulfur bond. So those dipoles don't perfectly cancel each other out. Likewise, if I looked at a tetrahedral molecule, the methane molecule is completely symmetric. Those CH bonds all have dipoles. Actually, they point slightly toward the carbon. They point toward the more electronegative element. And those all cancel each other out. But if I were to replace one of those hydrogens with, let's say, something that's not hydrogen, like a fluorine atom, all of a sudden you have 3 dipoles pointing toward the carbon, and then one much more significant one pointing toward the fluorine. That would be polar. It's just not symmetrically arranged. So we have to look for total spherical spatial symmetry, and that's a case where you have a non-polar molecule. So most things you see will have some asymmetry and are polar, but in a lot of cases it will be non-polar. Okay, the main takeaway from today was that there are 5 electron geometries, and within each of those categories there is several other geometries that we call molecular geometries, or just shapes. We use that word interchangeably with molecular geometry. And these give us a sense of the physical properties of these substances and the chemical properties of these substances.